All right. Welcome, everybody, and welcome whoever's on Zoom as well. Um, Today we have Gabe Kaptchuk visiting us from down the street in CS. He's an assistant professor in the CS department. Um, he's a theoretician. They got super curious about HCI, and so you call it applied cryptography is your field. Um, and previously, he was a research assistant professor at Boston. Got his PhD and MS in CS from Johns Hopkins, and very excited to welcome Gabe. So please join me in welcoming Gabe.
Yeah. Thanks for having me. Um, yeah, I'm excited to talk about differential privacy today. Um, I think it's an important piece of caveat that I really am not actually an HCI person. I'm really really an applied cryptographer who just got a little bit too curious over and over and over again until now I spend a lot of time with HCI people. And I'm kind of the least qualified and from an HCI perspective of everybody in my little research group that we work on. So um, that's just like an important caveat. And hopefully it will not impact your enjoyment experience of the talk, but I just wanted to put it out there very explicitly. So um, picking up on this theme, right, I'm an applied cryptographer, so it's not immediately obvious why I should do anything touching HCI at all. And to start this talk, I'll give you kind of my initial touch point where I started getting too curious, which was in the mid 2010s, 2016, 2017, Apple really started pitching themselves as a privacy first company, and this was going to be their entire way of kind of pitching their products. And I, at the time, had just started my PhD and I was doing work that thought about end-to-end encryption. And so I was interested in this space. I was interested in tech policy too. And Apple kind of famously put up this billboard. What happens on your iPhone stays on your iPhone. And right at the same time that they had this billboard up, they also released a new kind of very low-key document saying all of your messages are going to be end-to-end encrypted, right? So if I send you a message, you should assume that nobody else can see it besides me and you. That's pretty good. Except, oh, by the way, we're really interested in learning about people's emoji usage. And so what we're going to do is we're going to gather some statistics on emoji uses within these end-to-end encrypted communication things. And for me, I was deeply confused by this, and I didn't really know what to think that much about it. So I like to think about this as Gabe as the average consumer model. This is the way that I first interacted with this problem, where Apple kind of said, "Hey, we are a privacy first company. We're going to keep all your data nice and private. Nobody will see it." And I was like, "Yes, this is totally wonderful. Everything is going great. Take my money." And then as I started to look into this announcement, again, this was end of 2017, where they were using something called differential privacy, which was not a technique that I'd particularly heard of before. I think maybe I'd heard of it, but I didn't really know what it was. It was kind of, I knew this offshoot of the cryptography world, and we knew the names of the people who wrote those papers, but we didn't really know them anymore. They'd kind of departed from our community. I'll tell you more about what differential privacy is in a second. But essentially what they were doing is they were going to be gathering usage statistics about different emoji. And then they were going to use that to train a predictive model so that when on your phone, when you went to the emoji screen, it highlights all those words and you can just one click replace them all with emoji. That was essentially what they were doing. Um, and so for me, I then kind of revisited this me as an average consumer model. And I said, okay, you're a security first company, but we want to know about your emojis. So, nobody's going to read your messages except kind of maybe Apple a little bit is going to read your messages, but not too much. And it was this feels like a very trivial and frivolous use of breaking my end-to-end encryption guarantees. I don't understand it. And they said, well, don't worry, it's still going to be private. We're going to use differential privacy. We're going to set the parameter to be 16 and everything will be fine. And I, as a cryptographer, was like, what the hell does this mean? I don't know how to evaluate what this system means at all. I don't know how to think about the privacy that I end up getting from such a system. And I really thought that if I didn't understand what was going on, there was a very high likelihood that nobody understood what was going on, besides maybe the 6 people who really understood differential privacy in 2017. And it turns out largely I was correct. Nobody really knew what this meant. And I got really sucked in because it felt like they were kind of pitching on privacy. This was going to be their marketing scheme. But then in fact, in practice, it was going to be less secure. So around 2019, 2018, I got really bugged by this. And I sent a cold email to Alyssa Red Miles, which at the time was a thing that one could do because she didn't have too many emails that she wouldn't respond to you, which not, great things about Alyssa, but, she's overwhelmed now by doing too much. And I said, hey, I don't get this differential privacy thing. I don't know anything about HCI. Nobody in my group where I was a PhD student at Hopkins does this type of usable security thing, but it seems wrong. And I think somebody should look at it. And she said, great. I recently been talking to another friend of ours, Rachel Cummings, who's a professor now at Columbia and does differential privacy research and thinks a lot about humans kind of ish, but in an algorithmic game theory way, not like full HCI way. The three of us should sit down and try and figure out what the heck is going on here. And so we started looking at this problem a little bit more. And over the last, I don't know, 8 years or so, the team of people that we work with now to look on this has really grown, including some PhD students who initially started working with us when they're PhD students and now have graduated. So our team involves lots of folks at a lot of different institutions. And I'm going to be drawing kind of broadly on a lot of their work and kind of giving you an overall sense of what's going on in this space. In particular, we've published some papers that kind of try to understand how to think about differential privacy when it comes to the interface between differentially private systems and human beings. And I'll kind of give you some ideas what those are. And then, of course, I'm also drawing from lots of papers by my colleagues. And this isn't even a full enumeration of what's going on in the field. There's there's 2 or 3 other research groups that are interested in this as well, whose publications I haven't put up here. So I just want to kind of highlight all this work that's going on. Okay, so in order to start the story, I need to tell you what differential privacy is. I can't quite get away without any math, so I'll give you a little bit of math, and then hopefully we can start seeing why this might be an interesting HCI problem in addition to being a good algorithmic problem. So differential privacy was originally proposed in 2006 at a deep crypto theory conference called TCC, which only the theory side of cryptography ever looks at. So it's a kind of a niche thing that nobody really usually reads. In fact, entertainingly, TCC recently got downgraded from a top-tier conference to a second-tier conference because nobody cites the work besides other theoreticians. So that's how fringe of a conference. I mean, it's a great conference. It's just fringe from the outside world. So I published this result, and the idea was, can we somehow come up with a formal notion of privacy that would allow you to still learn things from a data set? So you have a data set, you want to learn kind of aggregate statistics about the data set, but you want to be able to preserve the privacy of individuals in that data set. It seems like a very worthwhile goal overall. The problem is that this had kind of resisted nice definitions for quite some time. And so in 2006, they came up with this notion of differential privacy. And basically the way that this works is if you imagine a database with lots of people's information, this gets processed through some algorithm. This might be a randomized algorithm. And the output of that algorithm is some distribution. Doesn't really matter what this distribution is for the sake of what we're doing. And all differential privacy says is that this algorithm should have the property that if you were to replace any one entry in the data set with a different person's information and then ran it through the same algorithm, then the difference between the output distributions of this algorithm shouldn't change too much. Right? You can get some kind of bounded ratio between these two things. The idea is kind of we can limit the amount of information in the output that's really about any one person. Right? And this is a nice way to perhaps think about limiting how much somebody could potentially try and adversarially learn about somebody in the thing. This makes some amount of sense. There's some hand waving going on here. It's not a computer science talk unless you put a theorem statement on the thing. So here's a theorem, here's a definition. But thankfully, you don't have to read about this too close. I will say that there's many different flavors now of differential privacy. This is kind of pure differential privacy. But again, the top level idea here is it bounds the maximum amount that any one person's data can change the output of some function. And the kind of way to read this is that the probability that if you run some mechanism over the data set is in some maybe subset of bad outputs that maybe reveals something about people isn't that different. It's kind of bounded by this multiplicative factor of e to the epsilon from some other neighboring data set, which means it differs by one entry. There's a couple kind of nice ways to talk about this. DP addresses the paradox of learning nothing about an individual while learning useful information about a population. This is a nice way of that some of the creators of the algorithm, Dwork and also Roth, talk about. And importantly, this is a definition, not an algorithm. So any algorithm can be differentially private. There is no specific DP algorithm. There are mechanisms that we build that take an algorithm and make it differentially private. So that's the way to understand here. How do you feel about this? Okay, that was it. So this is great. This is 2006. And then people get really excited about this idea because it turns out there's a lot of times when you actually want to use something like this. And then if you look at this definition, you will notice very, very quickly that it is quite abstract. And it's difficult to practically understand exactly what it's giving you. In fact, it's not immediately obvious like what it's protecting against. Moreover, there's kind of it's bounded by this thing e to the epsilon. Turns out if you look at the math a little bit closely, this has no units. There's a parameter epsilon that has no units because it's a bounded ratio between two things. And also the things in the exponent. There's a lot of things about this that make it pretty difficult to actually use in practice. The big one being it's quite abstract. It doesn't talk about the specific set of attacks even that you could potentially try to run to identify people. That's completely abstracted out. And in some sense, that's a power of it because it's very general, but it makes it really hard to think about in practice what it's actually giving you. Okay, one more slide about the math you might want to know about differential privacy. The first is a theorem that actually predates DP, but from Kobe Nissim, who's at Georgetown, is on both papers. They proved this theorem that said, it's known as a database reconstruction theorem that says if an adversary gets enough sufficiently accurate queries to a database, think about these as linear queries where you just take some like, weighted sum over something like that, they can eventually reconstruct the entire database. This is like a proved result. There's a lot of like words that I'm glossing over. What does sufficiently accurate mean? Whatever. But it basically means if you ask enough questions to a database, you can eventually uniquely reconstruct what that database must be. And so what this inherently means is that you cannot have a differentially private algorithm that is deterministic. You need randomness injected into it in order to get a differential privacy guarantee. And so there are kind of two general ways that we actually build differentially private mechanisms in practice. The first is it's in what's called the central model, where essentially there's a data warehouse. They gather a bunch of kind of like plain text records just as they would before. But then when they're going to release an aggregate statistic, what they do is they first kind of compute some kind of like normal statistic. So they maybe the sum over a bunch of rows or the average value or something like that. And then after they compute that, they add some Laplacian or Gaussian noise to that value, where the exact parameters on that are calibrated very closely to the space of the data set and the computation you're running. It's not particularly important. So that's kind of one way of doing it. The other way of doing it is called the local model, where people locally kind of add some noise to their inputs, and then it gets sent to some centralized data repository, and they can just release normal queries to the data set because the noise has been added ahead of time. So this is really how we get differential privacy in practice. There are other models. They're not important for today. Feel okay so far? Okay. I'm done talking about math behind differential privacy, right? All you need to know is that there's some noise involved, essentially, and that it's not immediately obvious. There's some parameters in there that are a little tricky to understand what they give you. So in the years after DP was kind of developed, there was a bunch of algorithmic work which led to kind of a lot more deployment than you might think for what initiated as a TCC paper that nobody ever read. In particular, this idea of being able to get aggregate statistics out of information while preserving individuals' privacy was like the dream for big tech, right? They wanted to be able to use all your data, but they wanted to tell you that it was private, right? And being able to do these two things at once, differential privacy let us do this. So there are deployments at all these companies. Google deployed a bunch of stuff with COVID contact tracing that had differential privacy involved. Microsoft deployed some interesting telemetry stuff for Windows that they would gather data about usage statistics, something like that. Uber had problems where their internal data analysts kept on stalking people they knew. And so what they did is they changed the access that their data analysts got to the database to be differentially private. Apple has used this left, right, and center. I've already talked about the emoji one. They've actually used it in a bunch of other contexts as well. Facebook, interestingly, released a thing called Social Science 1, which was a ton of presumably low-level data about people's interactions on Facebook that could be fed to social science researchers to understand kind of like politically interesting things that were happening on Facebook, but they didn't want to just like release people's usage statistics, and so they made it differentially private as well. So this thing is getting picked up everywhere across companies. And moreover, there's also adoption by government. In particular, the 2020 census tabulation was released differentially privately. Asterisks, state level queries were exact, but all other tables were differentially private. The Social Security Administration is currently building a validation server where people can run differentially private queries against Social Security and IRS data. And then the Israeli Ministry of Health recently released a first attempt at releasing a differentially private synthetic birth record data set. So people could understand trends about how people are being born in the state of Israel. So this thing is getting picked up everywhere, despite the fact that it's quite abstract and hard to understand exactly what it gives you. And moreover, it's actually been provoking quite a bit of controversy. People are not so happy with differential privacy in the census. The idea of injecting noise into a census is very fraught. If you know a little bit of the history of the census, the idea is that we should really count everybody one by one. That's how the US Census is supposed to work. That's not how the US Census has ever worked. We've always done imputation and done kind of all kinds of techniques to try and figure out who's there. But the idea that we were going to release noisy counts was very, very controversial. And Jayshree Sarathi and Dana Boyd have both written a lot about this. Dana Boyd actually has a book coming out hopefully this fall that kind of tracks some of the controversy around the use of differential privacy in the census. So there's a lot of controversy around just using this algorithm at all. Okay, so that's kind of an intro to DP and what's going on here. From my perspective, there's a couple of interesting things that are worthwhile thinking about if you are going to deploy differentially privacy to users. In particular, there's a need for some form of transparency, which is to say differential privacy is there because it's supposed to give you privacy, but then you actually want people to understand the privacy that they're getting. It's not the same thing as end-to-end encryption. End-to-end encryption has kind of an okay short summary of what it does. Differential privacy, well, we're going to gather information about you, but we're going to inject some noise. What is that supposed to do, right? There's no short version of this. And from my perspective, this makes it potentially a very obvious risk for misleading end users. So they might share information in a way that actually doesn't align with their own personal interests. Additionally, there's actually a second really interesting kind of human to differentially private system problem here, which is how do we build systems that meet people's needs? That is to say, there might be a system in which we're not going to top-down decide exactly how the privacy is set and how the whole mechanism works, but rather we might want to kind of work with people to do some type of participatory design style thing to figure out, okay, does differential privacy solve the problem that you have? And if so, what should I set that weird epsilon parameter to be? How much noise do I need to add into the system in order for you to feel comfortable, right? So this is actually kind of a circular problem, right? We both need to convey information out about existing systems and we need to gather gather information in to design responsive systems to people's needs. It's worth saying that. Well, I'll go into this in actually the next slide. So these are going to be the two kind of major themes that I'm going to touch on in this talk that have been kind of central to the work that we've been doing. I do want to briefly say, like, why is this an interesting problem? Interesting, I think, one, it gets to be interesting for free because it's being used in practice. So that's kind of what I've given you so far. But I actually think that even comparing it to other forms of communication about noise, it has interesting properties. The first is that there's this very clear balance between the amount of privacy you get and the amount of utility you get from the data. The amount of accuracy is really what I should say. Because you're using noise, you're using kind of randomness as a way to mask people's individual contributions, that inherently degrades the quality of the data. And so there's multiple different stakeholders who want kind of contradictory things. Users want as much privacy as possible, and people who want to use the data want as much accuracy as possible. And so there's already a nice little kind of optimization problem to think about here. The second is that we actually know the noise distribution exactly. So unlike kind of naturally occurring data gathering phenomenon where you assume that you have some sampling error, but you might not know exactly what it is, here, those sampling errors still exist, but we have a new problem where it's actually, I have sampled from a distribution and I'm telling you what the distribution is, right? This is a weird setting and not one that kind of has occurred, at least to my knowledge, in other places. And finally, there's kind of no real clear consensus on exactly what the set of bad things that DP is trying to protect you against. I've kind of implicitly said you can't learn that much about people, but that's not a very clear specific thing. And so there's actually some controversy in trying to figure out exactly what you want out of DP systems is not immediately obvious. So I'll claim these three things, and hopefully by the end of the talk, you'll at least agree with me on some of them, and maybe you won't, and that's fine too. Okay, so what am I going to talk about today? I'm going to very briefly, I'm mostly going to focus on this first problem here, which is what does it look like for making progress on the transparency problems in differential privacy? That is to say, actually doing a good job communicating to people what the heck this thing is. Then I'm going to touch briefly upon some ongoing work we have, which is trying to think about that second flow, which is setting parameters responsibly to people's needs. And then finally, if we have time, I'll do like 1 or 2 slides on what I think is actually particularly interesting work that we've been working on recently, which is trying to take some of the insights that we've learned from trying to use differential privacy in practice and the ways it breaks down in kind of like stakeholder interaction and user interaction, and think about designing new theory that doesn't run into those same traps. So writing new math. And that's kind of, I think that's for me where the goodies are, but I think all of these are important parts of the same problem. Okay, good. Everybody's on the same page, or I guess happy enough. Great. Okay. So I'm going to start with talking about a couple of papers that we've written over the past 4 or 5 years that start talking about this transparency problem. So when we first looked at this problem, the thing we wanted to do is understand actually how are people describing differentially private systems in practice, and how does that set people's privacy expectations? So kind of more of a naturalistic observation style study. And the reason we did this is actually just like even briefly looking around at the descriptions of differential privacy, you'll see radically different ways of describing the technology, or let's say both the technology and the privacy guarantees it gives you. So Census wrote what is perhaps my least favorite description of differential privacy of all time, where the entirety of what they said when they first released it was differential privacy, the new gold standard in data privacy protection. That was basically all they told you. They didn't tell you what privacy it gave you at all. They didn't tell you how it compares to anything else. They just said it's the gold standard, leave us alone. They ran into some problems for this one. This was not their best choice. We also see other types of descriptions. These are from news websites describing differential privacy as an algorithmic scrambling of individual user data, something like that, which sounds very similar to a lot of the encryption stuff that we use, but it's not the same technology. Differential privacy algorithms apply to data set. The links between people and their data get blurred. These are some ways that we saw it too. Differential privacy, which alters the numbers but does not change the core findings. So it tells you about the way that you can use it potentially, but nothing about the math whatsoever. Differential privacy allows general statistical analysis without revealing information about a particular individual in the data set. This is getting closer to the guarantee, but again, it kind of does this up to the fact that there is actually some leakage, right? That you do learn something, just how much is not clear. There's a whole bunch of kind of, this is mostly stopped in the last couple of years, but in the late 2010s, early 2020s, there were more kind of startups that thought they were going to solve the data problems in the world, even before like we were in our modern AI data problems. Like what we're going to do is we're going to have these data banks that we gather and make everything differentially private. It'll be great. And so the ideal implementation, the risk remains close to zero. So this was like marketing pitch that they had as a way to give people things. So we were seeing all these different ways of describing differential privacy in practice. And so we wanted to understand how do people understand these things when they encounter them in the wild? And so we gathered a whole bunch of these, some from industry, about 70-ish or so from out in the real world. This was the original data collection was done in about 2020. And since then, there's been a lot more DP deployments, hopefully some informed by our work. So it's no longer, I can't really include those in the gathering. And what we did is we kind of did a thematic analysis to understand what are the big descriptive themes that we were seeing in these. And then we synthesized some representative descriptions of differential privacy that we thought captured the core kind of things that we were seeing. And we actually showed them to people in a large-scale prolific survey to understand, and then ask them a bunch of questions, right? If the system was described in this way, what would you expect, right? What are the types of security properties that you might gather? So forgive me for throwing a large odds ratio table at you. But essentially, the quick way to read this is we had a bunch of these different descriptions that focus on different types of things. So the unsubstantial is the gold standard one. Techniques talk about scrambling the data or adding noise. Enables talks about the different types of analysis that you're able to do with differential privacy, et cetera, that type of thing. And then we asked them the different types of potential information risks, disclosure risks, right? So we, for instance, asked people, do you think that a hacker who got access to the company storing your data would be able to see your data or not, based on the description that you see? And we saw that indeed, particularly when it came to hackers, a lot of these descriptions did significantly increase people's confidence that a hacker would be repelled from the system. If you think back to one of those first slides I gave you, it actually depends in a very heavy way on exactly how you implement differential privacy. You can have differential privacy which protects against hackers, or that doesn't, depending on exactly where you add the noise, right? So it's not immediately clear that higher people thinking that they have higher privacy expectations around this particular information flow is a good thing. It's not clear at all. So other types of things. What if he was a data analyst inside of the company? Do you think they'd be able to see your individual data? The graphs that are released that detail information that they gather in aggregate statistics, do you think that might disclose information about you? Something like that. So we went through and do all these things. I'm not going to go into the details here. The kind of interesting thing to look at is as you look at rows across this table, you will see that some descriptions, they raise kind of people's privacy expectations for different types of disclosures. Even though from a technical perspective, almost all of these are the same disclosure risk, which is to say somebody looks at the raw data that they have inside the company. That's it. Graphs is the kind of odd one out, which has to do with like publicly published stuff. And so that means that some descriptions were setting people's expectations in a way that's somewhat incoherent with respect to the concrete system. So I'll kind of leave that at that. There again, you don't have to look at the super details there. We then went around and we asked people, okay, are you more likely to share your data, essentially, if you see one of these descriptions of the system? And we saw that basically there was nothing statistically significant, that any description that we gave people did not significantly raise people's willingness to share their data, which is interesting, right? Because I just told you before that it does raise people's privacy expectations, but then the next thing I'm telling you is that, but it doesn't actually make them share any more data, which is weird. Depending on exactly the type, we did one medical scenario, one salary data scenario. And so that actually was significant between how people shared data. So we had to kind of think this through and understand like what the heck is going on here. And we kind of came up with a way of thinking about this where there's a kind of pipeline here. There's some description that you see that might raise some expectations. And if the right expectations are raised, that might change your willingness to share your data, right? But importantly, these are separate steps, right? Users respond maybe to better expectations, and users' expectations are raised with respect to better descriptions, but the end-to-end doesn't work. And why can we see this? Let's work through an example. Maybe our first description here focuses on differential privacy allows analysts to know useful information. So this is what it enables without compromising an individual's privacy. This is kind of vague. And when we show people this description, we saw that this raises some expectations, but not all, right? So their privacy expectations around like data analysts went up. But then we might have a user who really would only share their information if they had higher confidence that their information wouldn't get leaked to like hackers or law enforcement, which has nothing to do with these other things, right? So here, there's no increased sharing. And so we kind of see as the entire ecosystem is kind of very haphazard as described. And we're not doing a good job of describing it. I think, no matter what the details of this are, we're definitely not doing a great job describing this because something weird is going on here. Seem somewhat good? Okay, so this was kind of a starting point, and it was a starting point for a lot of the field. There's kind of one paper that was published at the same time as ours, looking at some version of this problem. But this was kind of the first time that people had tried to HCI differential privacy, and people immediately said, "Uh-oh, we got to do something better here." So that led us kind of after that paper to think about what would it look like to develop better descriptions, better transparency around differential privacy. It seems like the obvious thing to do. And we did this in kind of two steps. One, we zoomed in on this deployment model. So this local versus central, when exactly the noise is being injected, can we design some kind of documentation that clearly sets people's expectations in a nice way? And secondly, we wanted to communicate this thing about there's this magic parameter and it determines how much noise you have, but don't worry too much about it. And these were kind of two separate steps that we took. And then finally, I'll touch a little bit more on not only data subjects, but also data users, where things are a little interesting. So these are kind of separate. That's not Usenix. That should be Kai 26. Slides are wrong. Okay, so we're going to start with the first and move from there. So the first thing we did is we wanted to understand how we could maybe potentially describe deployment model better. And so we did a kind of like iterative design process where we did some interviews where we kind of came up with different ways of showing people these guarantees. And we then eventually designed our own things. They're very heavily influenced by nutrition labels for privacy, which if people have touched kind of any of the privacy communication things is a starting point for a lot of folks. This was back in 2009. So the idea is we could kind of make these nice visualization things, a nice thing that you could see and work through where there's different information flows in each row. And here we took those same types of information disclosures that we had worked with in that previous paper. We did some amount to justify that there weren't any that we missed. We still might have missed some, but we tried to do some surveys to figure out if there was anything that we missed, and there was nothing notable really that we saw. And And then for each of these information disclosures, we kind of said, what is the baseline? What would you expect if there was no privacy protection there? And then similarly, what would it look like depending on the way that we've implemented our system? So in local differential privacy, this kind of protects against all of these information flows, whereas central differential privacy doesn't fully stop all of them. It stops very certain ones, but these others are still possible. This isn't a guarantee you get out of the system. And we ended up, we did another kind of prolific survey. We showed a bunch of people these and tried to measure the extent to which they felt comfortable with the information they were receiving and tried to measure their expectations. And as you can guess, like we're kind of teaching to the test here, right? If we ask them, like, do you think that this will protect against disclosure to law enforcement? Like the answer's on the table. They can read the thing. So we think that this is an important thing because this highlights the important information flows. Evaluating it is like a little tricky from a methods perspective. So I still think there's something open here to understand. Interestingly, in this study too, we also found that people really liked if there was some amount of text that described, at least in a high level, how it worked. They felt a little unnerved if I just told them this is the information flows and how they're protected. It's magic. Rather, they wanted to see some kind of low-level text, and we saw that this improved the trust that people felt in the system. So that was an interesting finding and one that we've kind of taken going forward as we describe differentially private systems. Don't just do information flows, also give people at least some flavor of the underlying techniques. Good. So this was how we went about thinking about these communicating the model. Things get a little bit trickier when you start communicating about epsilon. So let's take a moment. I told you back that you get this kind of like bounded ratio between two data sets. And how big that bound can be is determined by this parameter epsilon. So it's e to the epsilon, so it's an exponential thing, which is like horrible. Smaller values of epsilon means there's a smaller bounded ratio. So there's less information leakage. Big values of epsilon, you can have very big differences based on one person's data set, so it leaks a lot of information. It's the intuitive way to think about it. So we need to some way to describe to people like what you're getting here, right? Because a same system with epsilon equals 0.1 and epsilon equals 10, remember it's in the exponent, e to the 0.1 or e to the 10, are like radically different in terms of actually how much privacy protection you really get out of the system. So we need some way to communicate that. So this is a project led by Priyanka Nanyakara, who is now postdoc at Harvard, who's a viz person. And basically the challenge here is how do we communicate this in a visual way that is best practices. And so we kind of came up with 3 ways to do this that we then went and tested, and we tried to evaluate whether or not these were good based off of both some kind of objective measurement about like how well can you compare 2 systems and this one is better than that one, which is a little bit weak, but it's the best we kind of have. But also in terms of self-efficacy, right? How do people feel confident? Do they have enough information to make a decision, something like that? So we kind of evaluate on both of these. I'm also going to focus on these bottom 2 odds-based text and odds-based visual, but I'll just say we also had this example-based where we kind of gave you some examples about what potential outputs of a differentially private mechanism might look like. And remember, these are randomized algorithms, so you have to see multiple samples. You can't just see one. One is not meaningful. So I'll focus mostly on these other 2. These were kind of our text-based ways of talking about differential privacy. We'd said we wanted to kind of isolate the decision that the reader would have, right? So we're imagining some kind of information sharing scenario. And so we wanted to highlight, well, there's 2 different things that you could do. You can either share your data or not share your data with this particular system, which has some value of epsilon. So again, that's the first thing we did, is kind of isolate the decision that somebody made. And then we kind of use this frequency framing, framing the probabilities of some kind of disclosure happening with a frequency framing rather than using percentages, which hopefully follows a lot of best practice literature, particularly in security and privacy. And this is okay. There are some problems with it. In particular, we talk about there's an adversary A who will believe that you responded a particular way, that shared a particular piece of information. Actually computing this is very wonky. You actually have to assume that the adversary has a particular amount of auxiliary information, and you're basically doing like a bounded Bayesian update. Not great, right? That's not the best, but it's kind of the best we could try to do to take something abstract and make it concrete We had to make some assumptions about the scenario. The nice thing that this is generic and kind of computationally easy to do. So you could potentially adapt it relatively easily to somebody's particular context, right? Well, what do you think the information that they have is, and then try to do a Bayesian update on that. So it is kind of generic in that way, but it's still not my favorite. We also used these icon arrays, again, pulling on kind of best practices for communication in the visualization literature to show people, this is what happens, what it would look like if you don't share, this is what it would when you do. This is obviously a little confusing, right? If you don't share information, people still might think that you shared information. That's because it's a randomized algorithm. It kind of has to. But so it's actually just leaking kind of the additional information about you. So it's still a little complicated. We're not quite there yet on this. I'll just say kind of at a very high level what a takeaway from these two studies were. So we use these privacy labels. They seem to improve people's comprehension when it comes to these information flows, teaching to the test a little bit. And then adding this process text helps people feel more trust and confidence in the system. And then we have this kind of visualization-inspired technique for trying to communicate guarantees about epsilon. What we saw when we then actually ran a bunch of these and asked people how they felt about them, this definitely improves people's comprehension based compared to kind of like the old descriptions that we were seeing that really didn't touch on probability at all. So you'd hope it would improve. Interestingly, it also improved people's feelings of self-efficacy. They felt confident they had enough information to make a decision. So that I think is a relatively better measure. One nice thing that we were able to see is that we could, because we gathered enough data, we also asked people's willingness to share information. So, okay, would you share your information with this system, with this guarantee? And the interesting thing that we saw is that we did see a nice varying with epsilon. So as the guarantees of epsilon got better, people were more willing to share. As they got worse, people were less willing to share. So at least we're communicating something here, right? There's some responsiveness to our description. So something's getting better here. I'll say this is now kind of an ongoing big literature about how the heck you're supposed to communicate this thing. And it pulls on some of the work kind of in HCI more broadly around communicating uncertainty, but also a lot of stuff in the visualization literature in terms of how you communicate these things. So there's a lot more work going on here. One thing we were also particularly interested in was not only when it came to users. So the way that this kind of transparency thing works on the user side is, we say, okay, here's how the system works. And then they say, okay, I'm going to share my data or not share my data. That's kind of like the locus of decision. When it comes to data users, on the other hand, right, we give them some documentation that says, okay, here's a bunch of data. It's had some noise added to it. It has some parameters. Now download the data and have fun. And this is not necessarily the most pleasant thing in the world, right? Because you know that there's error somewhere in your thing, but you don't necessarily know how to account for it correctly. And so it turns out nobody had really designed any good documentation when it came to using differential privacy data, particularly for non-experts. And so we went around and we looked for an opportunity to study what it would look like to produce good documentation. And what was really nice is we found a natural experiment that we could use. The Wikimedia Foundation has for a while been publishing page view counts by country. And for a long time, their way of thinking about this is that they wanted some amount of privacy in this thing because there are very low frequency events that you wouldn't want to just report, in general. So for instance, somebody reading, the Malaysian language page in France or something for a particular thing, that's a low frequency event, generally speaking. And so you might be able to guess, oh, that was probably that person. Right? So they want some amount of privacy on these counts that they output. And so what they've been doing for quite some time is they've used rounding and suppression. Right? These are kind of like the standard things you do. They round everything they round up to the nearest, let's see if I have the number, and then they suppress anything below 1,000. Then about 2 years ago, they started a process where they were going to replace that with differential privacy. The reason being differential privacy, because you know the noise distribution exactly, you can actually do more accurate statistical computations over differentially private data. So this was done by basically, there was like one person inside of Wikimedia who was told, hey, we should do this differentially privately. Do you want to go for that? His name is Hal. Hal is great. Hal went and did this whole thing. And then he was in charge of also producing the documentation for this. And he came to us after seeing our first couple work and saying, like, I don't know how to document this. Nobody knows how to document this. Like, what should we do? And so we sat down and we were actually able to do kind of a natural experiment where we looked at people's understanding of the data and thinking about noise when it was done with rounding, and the same data that was done with differential privacy. It's the same data set on different years. So it's not exactly one-to-one the same, but literally the same data schema is the same. And so what we did is we produced some documentation between these two things and then did hour-long interviews with data users who are familiar with Wikipedia data already and had them do 3 relatively simple data analytic tasks over this noisy data. The first, they had to compute the max value, so which is the page which has the most views in a particular time frame. The second one was the mean value, so what is the average number of views this groups of page has. And finally, the last one is, do 2 different pages have the same number of views? And all of these, they're working with noisy data, right? So we also wanted them to reckon with the fact that it's noisy data. And so we asked them to compute 95% confidence intervals around their answers, right? And this is where things get messy, right? If you just want to, I can report the data. This is like very simple Python, but then to also understand how the noise that I added influenced these confidence intervals is a little tricky. You have to actually kind of know what you're doing. So, okay, the first thing we did is we produced some of these visualizations. I'm going to try and, well, now I can't find what I was doing. Crap. One sec, pause, pending. Go to JShree's website. Boop. I just want to show you briefly some of the documentation we created, which I don't know, I think was quite good. So we kind of went through and we gave people some interesting information about the data set, the data set schema, where the privacy protection was applied. We gave them some kind of visualizations in terms to understand how this noise was added and how they should think about it a little bit, as well as some information about the accuracy of the privacy protection, exactly how it worked. And we produced kind of equivalent versions of these, one for rounding and one for differential privacy. And then we kind of hide some details about how exactly DP was generated there because the math is a little ugly. But this is kind of the thing that we produced. So if you're interested, it's up there. I can send you the link later, or if you want to go to Jayshree Sarathy's website, it's just up there. Okay. So then we ended up doing this interview study where we talked to 15 people who had previously been working with Wikimedia data. As an interesting aside, we got some, for those of you who I'm sure have experienced this too, we got some people who had no idea what they were doing. And I just filled out our survey and tried to just ChatGPT their entire way through the hour-long interview. So we had to throw out some data, which was an interesting thing to encounter. But the results were somewhat interesting, at least in me. So generally speaking, users found the rounding much easier to understand, which is not that surprising because we've all encountered rounding before. But differential privacy they found much easier to mathematically reason about. So this is good, right? This means that at least something has gone right because this is what we want in some sense, is people to be able to do easier math on it. And these are some quotes, right? The rounding is mathematically easier. It's like high school math versus college math. The rounding is easier to explain, but feels statistically fraught somehow. In particular, if you're trying to compute confidence intervals over rounded data, dear Lord, right? Because all the data is rounded up in a biased way, and it's just like a whole mess. So there's good reason to see that. At the same time, people really struggled to compute these confidence intervals, particularly when they were doing something like an average. So they're taking an average over multiple data points, each of which was independently perturbed from some known distribution. So of the 15 participants, only 3 of them correctly computed it. And of those 3, 2 of them had recently taught statistics courses, right? So they are like as like right-tailed as you can get in terms of their expertise. And we were seeing people who are normal data users, like, this was really, really tricky. I had to sit down and do this when we were designing the tasks. I want to make sure, can I do this well or not? The first solution I gave was wrong. And then I said, wait, no, do some hypothesis testing, and I had to work back around, and I could do it. But, as somebody who stared at this for a while, my first instinct was also wrong, right? So there's still some more work to be done here. Interestingly, as well, when people kind of compared the two methods, there was an interesting conflation between how accurate it was and how private it was. Right? In particular, they looked at differential privacy and said, well, this is more accurate. Doesn't that mean it's probably less private? Actually, in a formal sense, that's not strictly true, right? We actually can't prove anything about the privacy guarantees of rounding at all. It's very, very tricky to even think about this. Differential privacy gives you actually a better privacy guarantee as far as we understand, but because it does it in this particular way, you can reason about it more accurately, right? So there's this interesting conflation where it's like, well, it can't be private because it's too accurate. So there's something interesting going on there as well. And finally, I thought this was interesting when people are asked, like, okay, which one do you use if you're going to publish a paper? And they're kind of like, well, we got to use DP because I can just cite a whole bunch of papers that say DP is the correct thing to use, right? And so this has nothing to do with the underlying techniques. Also, right, DP sounds sexier. It sounds like a little smarter if you use DP, right? So there's something interesting going on here culturally within the data user community where they know differential privacy is a thing that they're supposed to use or that's supposed to help them. But it's not immediately obvious that it's easy to use, right? So there's obviously still a usability gap here that we need to work with. Okay, I have no idea how I'm doing on time. Oh, easy, no problem. Okay, so I'll just briefly touch on these last two things. So this is some ongoing work that we're doing right now, thinking about how do you, from a participatory perspective, go about setting these parameters responsively to end user needs. The ways that we're thinking about doing this are, one, we're thinking about eliciting some kind of mechanism to elicit people's parameter preferences, and then think about plugging that into some kind of mechanism design thing. And then I'll say a little bit more about why that might not be the best choice at the end. So the first thing that we have ongoing right now is that we are using a tool from largely the marketing world, this thing called conjoint analysis, where at least I think about it as a marketing tool, where basically the idea is I'm going to have a respondent come into my survey, and then we're going to say, okay, here's the scenario. There's one of two different systems that you could potentially have. Which one would you prefer? And this is oftentimes used in the marketing world, like you want a car, but you don't want to produce every possible combination of features and colors and whatever. So you'd use this conjoint analysis to figure out what are the key things that people care about the most in a system. And so we're kind of abusing that same methodology to allow us to understand what are the properties that people care about within a differentially private system. And then we're going to be able to kind of understand how to maybe optimize some of these things. So the way this conjoint works, basically there's two different options. Option 3 is opt out. And there's a bunch of different features of this system. This is not exactly what we're showing people. We're not just saying like epsilon, that would be evil. But instead we kind of compute like descriptions of these various different properties. And we say, okay, you know, would you rather use system 1 or system 2? And they choose one of them, and they get something like 30 of these comparisons back to back. And then we ask them across subjects with a bunch more people. And then there's some optimization solver that tries to compare these things to each other. I will say that for the work we're doing here, we're focusing on what we hope is a slightly more realistic setting, where the actual computation that's going to be done is not like an average. It's like we're computing a regression model or something like that. So there's some type of ML, broadly construed, that's going to be happening with your data. And that requires us doing a whole bunch more math to figure out actually how to convert epsilon into probabilities of attack failure, attacks working or not. Very, very messy, very, very messy math. Anyhow. So this is ongoing. We haven't done data collection yet, but we've refined our instrument, and hopefully we'll be doing so soon. We're basically the student who's leading this is currently on the job market, so we have some buffering problems that we got to deal with. And then our hope is after that to kind of take the results we get from such a thing and plug it into some kind of multi-stakeholder setting. So we have somebody on our team who's an algorithmic game theorist. And so the obvious thing to do is build some kind of mechanism that optimizes for things or something like that. We haven't done this yet, but this is kind of where we're hopefully going next. When we initially did this and described this, we then were at the time bringing on Dana Boyd and her PhD student, Jay June, who are both sociologists into our program, into our kind of research group. And they very reasonably pointed out that there are a lot of barriers to participation that you probably can't just solve by throwing mechanism design at it. That's probably not going to work, right? So even looking at things like who gets to have an opinion in the conversation is obviously an important part of the problem. So they're doing a bunch of really interesting work also looking at the ways in which organizations actually solicit input. And what are the barriers to doing this kind of participatory design at all when it comes to some kind of differential privacy deployment? So Jay June, I think, is going to be embedding both in big tech companies using DP, but also in the Census Bureau. And Dana, as I said, her book is coming out in the fall looking at DP in the census. So that's kind of very high level where we're going with some of this as well in order to kind of get that second part of the flow. I wouldn't be like a mathematician if I didn't try to sneak some math back in at the end of my slides. So here we go, a little bit of math. One of the things that I find particularly interesting from having spent a couple of years doing this work is that some of the fault here needs to be put not on like people who design bad descriptions. Some of the fault is just differential privacy's fault. It is a very general definition, and it's super powerful because it's general, but it's impossible to reason about. Like after years, I still don't know. If you came to me and said, hey, I'm going to use epsilon equals 4, do you want me to share your data? I'm not sure yet. I was at a DP workshop last year where the entire room is 50 differential privacy researchers, and somebody came up to the front of the room and said, hey, would you rather donate your information if the system is using differential privacy with epsilon equals 10 or k-anonymization with k equals 4? And nobody in the room could answer the question. And these are people who really wrote the paper on differential privacy. We're in that room. It's totally goofy, right? So we need some type of rethinking about our algorithmic layer and trying to reimagine that work from kind of like a base starting point. So again, like in my mind, there's a problem with DP. It's incredibly powerful because it allows the protections to be abstract. And you can't really say exactly what it's not instantiable, right? You can't say exactly, it protects against all adversaries with all auxiliary information. It's very worst case, but that doesn't let you understand what actually would happen in practice. And it doesn't instantiate the attacker very well. So largely this generality at the cost of specificity and usability is just baked into the underlying definition. So with a couple of other folks who are much more on like the core DP side, we started thinking about this problem for a while. And we're trying to think about what would it look like to reinvent new theory that might not have some of the same problems. And we kind of narrowed in on this core idea that DP, for better or for worse, it flirts with the idea of being a sufficient privacy notion, which is to say, oh, you use DP, you're good to go. That's it. That's private. And it doesn't necessarily, if you ask people who are experts in DP, they will not say this to you. They'll say, well, it's really part of a larger system, whatever. But the way that it's being talked about in practice, it flirts with that idea. The generality makes it seem like use and forget. That sufficiency notion, the kind of opposite of that, would be what if we had a set of privacy notions that didn't aim for sufficiency? They didn't say against all adversaries. They didn't try to be really, really general, but instead we could think about them as necessary, right? If you're going to have a data release, it probably should protect against at least this attack, something like that, right? And if we had enough of these necessary things, we could potentially use them to try to evaluate a potential choice of DP parameters to say, well, how good is the protections you're actually getting, right? We're trying to make things concrete here. In a way that this isn't, right? And in particular, this generality, right? It must be general. This gives an opportunity to be concrete and specific. So along the way, while we're thinking about this, we came up with a notion. I just really like this phrase, and so I'm going to keep pitching it whenever I can. The idea of an ergonomic definition, which is to say we have notions of usable definitions. Usable definitions tend to be kind of pointing to the non-theoreticians, right? If I have a usable notion of privacy, then I would assume that people understood that. Data subjects or data users would understand that notion. Ergonomic kind of says, okay, let's get that. And it should be rigorous enough that theoreticians can prove theorems about it, right? If it's only usable to k-anonymity, very understandable, right? Very understandable. Horrible to prove theorems about. Just the absolute worst thing you could possibly imagine, right? And so we have this notion of a kind of two-sided usability, as it were. Right? So it's usable when you're trying to do the theoretical work, the underpinnings to actually realize this formally and prove theorems. But then it also has nice usability when it comes to trying to convince stakeholders that this is a good idea. We should probably use this, right? We should probably have a system that at least guarantees this type of privacy, or you're trying to build intuition about how good your privacy guarantee is. Weirdly, I have not seen this idea before, which is weird. It seems like it should obviously exist. And maybe I just don't know where it is, but anyhow, that's what we had. So we set about actually trying to build one such particular privacy notion. I am not going to go into the math because it's there's way too many continuous. There's integrals. I only know how to do summations, and I would to use some actual information theorists to do the math correctly. But here's our idea of called demographic coherence, which we think is a very nice and natural notion of privacy that systems probably should have. The idea is very similar to holdout testing with machine learning data sets. So you train your model on one set of data and you test it on the other. You kind of assume that it should kind of perform well across the two. So that's maybe one way to hook into the idea here. So the idea is I have some data set and I want some kind of data release process that's kind of happening here which ensures that if I took the data set and I split it in half randomly, right? So I kind of have my XA here, which is, you can think about as your training data set intuitively, and then some XB here, which intuitively is like my test data set, something like that. And I run kind of only XA through the process. And then I hand it to some arbitrary learning algorithm, which is going to make predictions about things about people in the data set. That's it. Right? So you can imagine making this very, very concrete. The slides that I took this for, if people are familiar with the the Netflix IMDb database reconstruction attack, we kind of use that, right? There's some kind of data that gets collected by Netflix, and then some learner is trying to predict features about people based off of the fact that they have some information that's in IMDb and in Netflix, something like that. And I have, right, this predictor is trying to guess whether or not particular people have a characteristic, something like that. And then what we do is we basically chart the performance of our predictor on XA and XB. Right? And we just see how different they are. That's it. And intuitively speaking, right, if you can't learn that much about anybody in XA, then you should only be learning kind of like data set level properties of XA, then you should perform roughly the same on XA and XB. In particular, we split these two parts of the data set randomly. Right? So if you could really differentiate between these two, you could probably reproduce the randomness that was used to split them apart. That's the information theory way of thinking about it. And so we basically kind of chart these two things and we measure the distance between these two distributions. We happen to use a particular notion of distance called the Wasserstein distance, whatever. Again, like we were trying to make this nice for theoreticians to use, so I'm suppressing some details that make it nice in that way. And we formally study this privacy notion. We show, somewhat unsurprisingly, that differential privacy immediately implies this. So, you can actually just get this immediately by making your system differentially private. But what's really interesting about it is you can express the privacy guarantees that you get from DP using this language. We can say, oh, you're afraid about a large learning, some large model trying to predict whether or not you're queer based off of your movie watching habits. We can bound the probability that happens, right? And I can tell you exactly what parameters of differential privacy mean in this setting, right? So we get a nice kind of like one-to-one correspondence. There's more math to be done. The bounds are actually very loose right now. It's really hard to prove things in a tight way, but it's nice. It also has some nice experimental kind of use cases. It's very cool, but I'm just going to leave it at there, very high level. And if you're interested, I'm happy to talk a little bit more about it later. Okay, so that's all I got for today. So hopefully there's kind of three things, right? We've built some interesting transparency approaches. I think they're pretty good. There's obviously still more work to go to do there. Two, we're hoping to build some interesting parameter selection tools using this kind of more participatory way of thinking about things. And finally, I think differential privacy, because of all of its usability challenges, provides some nice opportunities for building new algorithmic theory. And that's kind of an ongoing and open-ended process. So I'll stop there and say thank you so much for your attention. I meant to say you can ask questions anytime, but I didn't say that at the beginning, so sorry. But yeah.
We got 2 minutes on the clock, but are you sticking around after? Okay. Yeah.
Hi, Gabe. This is Wentao. I wanted to ask, so you've done a bunch of work on, you and others have done a bunch of work on transparency around differential privacy. Real world differential privacy deployments, by and large, have used very large epsilons. Do you think that for good and also questionable reasons, do you think that the transparency mechanisms that you've worked on would be any use in those cases other than just showing that maybe like the privacy guarantee is kind of meaningless, or is there still any use to that?
Yeah. Okay. So there's a bunch of stuff that I hit under the rug, which Wentao was talking about, which is basically, if you think all the way back to like slide number 1 that I showed you, Apple, when they deployed their system, they set the bound between these, the max amount of information that you can learn is e to the 16. Huge number, absolutely ginormous number. And actually, interestingly, their deployment totally borked it, and they refreshed their privacy budget every day. It was just like so unbelievably broken. It was funny. So yeah, in these types of settings, if you plug in the math essentially to say if you go to these like icon arrays, and you are going to say like, okay, if I plug epsilon equals 16 into this icon array, like, what does it look like? The answer is like, it's 100% on all of this. Like, there is no privacy at all, right? It just falls apart. Yeah, so I don't think our transparency does anything in these settings. I think it's basically, I would say it's honestly would just be confusing. It wouldn't even be showing that it's bad. It would just be confusing because it'd be like, well, if you contribute your data, they'll learn something about you. And if you don't contribute your data, they won't learn something about you. It'll be something like that, essentially, which is, I think, is useless and confusing. I also think setting epsilon equals 16 might be useless and confusing. Like, I'm not sure it's our fault. I think it's kind of their fault. If you look at the theory literature, basically nobody knows what you get out of setting epsilon equals 16, right? So for instance, epsilon in the census, effective epsilon, if you convert from what they actually use, is like 19.6 or something. And it's split up. They don't use all of it in one go, right? So different data products have a smaller epsilon, but you're still talking like 5, 6, 7 epsilon or whatever. And the question is like, what privacy does that give you? Largely, if you talk to theory people, they say it doesn't. If you talk to applied practitioners, they tell you, well, let me tell you, the noise that I'm using really degrades accuracy, so it must be doing something private, which is a conflation. It's the same mistake that like our data users did, right? So yeah, the short answer to your question is like, no, I think they're basically useless. And I'm not sure that giving people tools to describe it will ever be helpful if we can't actually start to give better understandings of the privacy that you get, right? Like we're missing evaluative work to understand actually how to think about this at all before we can even start communicating it. Yeah.
Well, it is 1:31. So let's end it formally, but we can stick around for more questions. Thanks, Gabe. Thank you, people on Zoom. See you next week.